The lab experiment number 1 is dedicated to analyze stochastic processes. In particular, we'll start by reviewing in exercise number 1 the effect of the average of independent random variables. And because of this, we need to take into account the theoretical results of the law of large numbers and the central limit theorem. In particular, we are going to average initially in section A of the exercise number 1, we will average independent random variables with unit mean and unit variance, and we will vary the number of variables that are averaged. When the number of variables that are averaged are increasing, the mean is always 1, but the variance is becoming lower and lower. And here, each random variable has a Gaussian distribution, and the average has a Gaussian distribution with unit mean. This is very intuitive. But what is more interesting is that the same result is going to happen even when the random variables that we are averaging have not a Gaussian distribution. In this case, we'll average uniform random variables between 0 and 2. This means that the mean is again 1. Again, when the number of random variables is increasing, the variance is reduced, the mean is always 1, and what is interesting is the histogram, because we have uniform random variables. The average of 2 produces a triangle in the PDF, the convolution of 2 rectangles. But when we are averaging more random variables, the distributions tend to be Gaussian distributions with mean equal to 1 and progressively with a lower variance. In exercise number 2, this random process is an stationary random process. Because of this, the mean is constant. The autocorrelation function has a shape like this. In this case, if we plot the autocorrelation as a function of tau for several different values of t, we have always the same value. And finally, if we average the square modulus of the frequency response of the signals that are in the random process, we have an estimation of the power spectral density with the DC term here, the delta 0, and the two deltas corresponding to the sinusoidal function. In section B, this random process is cyclostationary. Now the mean is periodic. Now the autocorrelation function is not constant for every value of t. Maybe this can be seen better in this picture for different values of t, and this picture is a figure of the autocorrelation as a function of tau. For several values for t, we have different signals, but all of them are periodic with respect to tau, with respect to t, sorry. Again, the average of the square modulus of the frequency response of the signals provides an estimation of the power spectral density of the random process. Finally, in exercise number 3, we will analyze the characteristics of the Gaussian noise. In this case, this noise has zero mean. The autocorrelation function as a function of t1 and t2 is only non-null when t1 is equal to t2, or what is the same, if we plot this autocorrelation function as a function of the difference between the time arguments, we have a delta function independently of the time instants, and the average of the square modulus of the frequency responses of the signals provide us with an estimation of the power spectral density that has a constant value equal to 1.